This lesson deals with the analysis of the differential amplifier. You can find these notes in the ECE201 ebook in Chapter 4, starting on page 30. Consider the following circuit that has 4 resistances, an op-amp, and 2 inputs. Now let's solve for the output as a function of these 2 inputs and the resistors that we have. Now since I have feedback around the output terminal back to the minus terminal, we can assume that our no voltage, no current property is true. We also have 2 sources, so let's use superposition. Suppose I set V2 equal to 0, and then find the output due to V1. And that's what's shown here on the drawing. But when I short V2, I have R3 in parallel with R4. Now this looks a little bit like the inverting amplifier, but I've got this extra term here. But what's going on with this resistance? Well, the current coming in here is 0 because I have a very high resistance from my op-amp, and therefore the drop across these 2 resistances in parallel is going to be equal to 0. So I could replace this by a short circuit, and I'd have no current because the op-amp has a very high resistance, and I have no voltage here because of the short circuit. So this would be an equivalent to our previous step. And now this looks like the inverting amplifier, and we can just write the answer down by inspection as minus R2 over R1 times V1. Let's set the other source equal to 0. Do the same thing. That would be a short circuit over here. And let's find the output due to our second source, which is V2, and analyze this circuit. Now, it may not look like this, but there's actually a non-inverting amplifier embedded inside here. Let me redraw this. So here I have V2 going to R3 and then R4 to ground into the plus terminal of the op-amp. So let me draw that over here. Let me rotate this op-amp, flip this over. What I've got then between the minus terminal and ground is the resistor R1, and between the minus and the output I've got R2. So here's our non-inverting amplifier. Now whenever we see this, we can replace this by the model that we developed, which consists of an open circuit, sensing a voltage, and then the output's going to be a voltage-controlled voltage source with 1 plus the feedback resistor divided by the resistor back to ground. V out due to the second source is just this controlled source, which is 1 plus R2 over R1 times the voltage V sub S. But what is V sub S? It's a voltage divider with R3 and R4. In other words, R4 over R3 plus R4 times V2 is V sub S. So now I've got the output due to the second input. I can add the 2 results together. Here's our first result, and here's our second result. Normally you just stop here and evaluate your resistor values and find the values of V out in terms of V1 and V2. But let me do some factoring again. Pull out an R4 from the numerator here. Let me pull out an R3 from the denominator. So then I would just have 1 here, and I would have an R3 here. So I multiply this back out to get R3 plus R4. Now suppose that I made the resistor ratio of R2 to R1 the same as R4 to R3. Then this term here would be the same as this term, and they would cancel. The ratio of R4 to R3 is the same as R2 to R1, and I have that same ratio here, but with a minus sign. What I've got is the difference of the 2 inputs times the ratio of R2 to R1, provided it's the same as the ratio of R4 to R3. The circuit is also called a subtractor circuit, where I'm subtracting one voltage from another. This too is a common circuit in electronics to building a variety of applications, and so let's see if we could develop a model for this. To develop a model, we have to find a circuit that has the same equations as this red blob. Let's just write all the things that are going on with the inputs and the output. So the rise in voltage here would equal the drops around the loop. If you apply a voltage here, some current is going to most likely flow. Let's call it I1. And so let's go around this loop then. Right? So it's going to be the rise in voltage is equal to I1 times R1 plus 0 plus the drop across R4. Same thing with V2 here. If you apply a voltage, most likely a current will come out of here. Just assign it a symbol, call it I2. But because this current is the same as this current, because the op-amp has no current coming in or out of it because of its high resistance, I could use the voltage divider rule here to find the voltage across R4. It should be R4 over R3 plus R4 times V2. So that's the voltage across here. And I can substitute that back into here. V1 is equal to I1 R1 plus R4 over R3 plus R4 times V2. So this is what's going on at the terminal where V1 is connected. For the terminal V2, the rise in voltage is V2, the drop is I2 R3 plus I2 R4. And I make up a circuit that does these 2 things. V1 is equal to a voltage plus a voltage, so it looks like I got 2 things in series. Now one of these is a multiple of another voltage, so I'll use a voltage-controlled voltage source to create this effect. And the current that's coming in here is I1. I have I1 times R1, so I'll put a resistor here, R1. So I create the drop across here, the drop across here. So the rise in voltage equals this drop plus this drop, and that's the same as this equation. The second equation looks like Ohm's law. If I apply a voltage and a current flows, where that resistance would be a single resistance whose value is equal to R3 plus R4. And then lastly, what is the output? Well, it's a voltage-controlled voltage source. Put any load you want here except a short circuit, and the voltage won't change. In other words, the Thevenin resistance is 0. I found that that was R2 over R1 times V2 minus V1. Where here's V2 and here's V1. Assuming that we balance this ratio. We're going to do this with a potentiometer when we build these in lab. And this is the analysis of the differential amplifier.